So we're in chapter 5, and we want to introduce section 2. Chapter 5 has 3 sections, and they're all about probability distributions. The first section introduced the idea of a probability distribution. And now in the second section, we are going to look at a particular kind of probability distribution called a binomial probability distribution. And then the chapter finishes in section 3 by looking at a different kind of probability distribution called a Poisson probability distribution. So just as a quick reminder then, a probability distribution that we introduced in 5.1, what does that look like? So we can have an idea in our mind as I then talk about a binomial probability distribution. A probability distribution is similar to a frequency distribution, but there's a little bit more notation involved. And so we're going to have, let me switch my tablet here for a sec. In a probability distribution, we have a random variable x, which must have some numerical value. And then for each value output of x, we have a probability of x. That's the probability of a given value of x as a result. So this is really hard to think about in general. So here's an example for specifics. And then hopefully if we keep this example in mind as to the idea of a probability distribution, then we'll look at a binomial probability distribution for this section. So in my example, which is an example that I gave in the introduction to 5.1, let's say you're going to roll a die and you're going to see what number you get. So then I could say let x equal the number on the die roll, on the roll of a die, and p of x would then be the probability of getting that number. And so I could make a table, which is called a probability distribution table, to show what this probability distribution looks like, in which I would basically list what my possible results would be for x. So if I roll a die, what could I get? I could get a 1, a 2, a 3, a 4, a 5, or a 6. And what would the probability be of getting each of those rolls? Well, the probability of getting 1 when I roll the die roll of a 6, since they're equally likely, is 1/6. And that's the case for each one of these numbers. Each one of these numbers has a chance of 1 out of 6 that's the number I get when I roll the die. So this is an example of a probability distribution. This is what a probability distribution looks like. It's a list of possible numerical results to some sort of a procedure, like rolling a die. And for each of those possible results, there's a given probability of a likelihood that you, by random chance, happen to get that particular result. That's the idea and an example of a probability distribution. So while we have this simple example in front of us of this idea, before I expand upon it for 5.2, are there any questions that anyone would like to ask or discussion to have about this while we have this example in front of us? Questions at all? Okay, so imagine as we move forward, when we're talking about a probability distribution, and then we start to talk about a binomial one in particular, that you're going to have a list of numerical possible outcomes, 1, 2, 3, 4, 5, 6, something like that. And in each case, there's going to be a likelihood that that number is the one that you get when you perform some experiment or some procedure. Okay? All right, so here's the key concept. The focus of this section is the binomial probability distribution. So it's a particular distribution like the one I just gave. The one I just gave was not a binomial distribution. And the methods for finding the probabilities. So here we're going to have a certain kind of a distribution and there's going to be numerical outcomes, but we're going to focus on how to find out what those probabilities are for that kind of for a binomial probability distribution. Easy methods for finding, we're going to also look at easy methods for finding the mean and standard deviation of a binomial distribution. Those are presented. And in other sections, we stress the importance of interpreting probability values to determine whether events are significantly low or significantly high, just as we did in other sections. So that's the key concept of the goals for this 5.2. All right, so what is a binomial probability distribution? Keep in mind, a probability distribution is what I discussed in our example. When it's a binomial probability distribution, this results from a procedure that meets these 4 requirements. So the procedure I gave before was I rolled a die and I got a 1, 2, 3, 4, 5, or 6. So we need to think about what procedure is used to get those possible numerical outcomes. And if it meets these 4 requirements, then that's a binomial probability distribution. And that tells us how we can calculate what those probabilities would be. So number 1, whoops, lost my pen. The procedure has a fixed number of trials. A trial is a single observation. So we're going to have something and we do it again and again and again, and we're going to do it a certain number of times. Number 2, the trials must be independent, meaning that the outcome of any individual trial doesn't affect the probabilities of the other trials. So we've talked about independent events in chapter 4. So for example, if I flip a coin and I'm going to get heads or tails, then I repeat that again. I do another trial of that procedure and I flip it again. Whether I got heads or tails on the first flip has nothing to do with whether I got heads or tails on the second flip. Or imagine you have a roulette wheel where you randomly get a number from 1 to 36 and you spin it and you get 7. Well, when I spin it again, the fact that I got 7 on the first spin won't affect the probability of getting one number or the other on the second spin. Those are independent events. Number 3. Each trial must have all outcomes classified into exactly 2 categories, commonly referred to as success and failure. So this is the idea that the bi in binomial means 2, like bicycle has 2 wheels. Binomial means there's 2 outcomes. There's 2 outcomes. So in the examples that I just gave with a repeated procedure, flipping a coin, there are 2 outcomes. I get heads or tails, and I could say heads is success and tails is failure. So that example of flipping a coin repeatedly satisfies this 3rd requirement. But the example I gave of spinning a number from 1 to 36 on a wheel and seeing which number I get, that has 36 different possible outcomes, not 2. So that does not meet this requirement. That would not lead to a binomial probability distribution. And then lastly, the probability of success remains the same in all the trials. So flipping a coin, if heads is success, and I do that several times, so I have different trials, and I either have success or failure, heads or tails. Well, the probability of success every time I flip a coin is 50%. And that's the same every time. So that also meets criteria number 4 here. So flipping a coin some n number of times is an example that would lead to a binomial probability distribution because it fulfills all of these 4 requirements. And it's usually the simplest one that people will keep in mind. So a simple example. Flipping a coin n times, could be 8, 7, 20, whatever, with heads being a success. So that's an example of a binomial probability distribution that would result is flipping a coin some number of times. So again, to be a binomial probability distribution, you have a probability distribution where there's some number and you have a procedure that happens a fixed number of trials, like flipping a coin 10 times. And 2, the outcomes must be independent. Every time I flip the coin, it doesn't matter what the other times I got. Every time it's a new independent result. In this case, my numbered result would be how many times did I get heads? Each time, the outcomes have only 2 possibilities, success or failure. In this case, heads is success and tails is a failure every time I flip the coin the 10 times. And the probability of the success in each individual trial stays the same. Every time I flip the coin, there's a 50% chance of success. So flipping a coin 10 times with a 50% chance of getting heads, that is an example of a binomial probability distribution of results where X is the number of times I got heads with my 10 flips. So the possible results could be 0 if I got tails every time, 5 all the way up if I got 5 heads and 5 tails, all the way up to 10 successes if I got heads every single time I flipped. And the 0, 1, 2, 3, 4, 5 up till 10, each one of those possible results from this binomial probability distribution will have some likelihood that it could occur. What is the probability that I would get heads 7 times? What is the probability that I would get heads 2 times? Something like that. So I know that's a lot to think about. Let's pause here and see if we have any questions. Can you ask questions if you're having a hard time understanding? Any part of these that I can explain better? In particular, anything about these 4 requirements that you need to be a binomial probability distribution? Any questions at all? Anything? All right, try to hang in there if you can. All right, so here comes some notation. S and F, success and failure, denotes the 2 possible categories of all outcomes. So you'll have some situation described like by flipping a coin, for example, and one of the 2 possible results we'll call a success and call a failure. And that doesn't necessarily mean the thing we're calling the success is in some way good. It could be if you are testing people to see if they got cancer and they either got cancer or they didn't, they might call getting cancer the success. It doesn't mean it's a good thing. It's just a label. So just pointing that out. S and F, success and failure, denote the 2 possible categories for all outcomes. So P of S will be the probability that the number of successes was equal, P of S is equal to P is the probability of success. So for the coin example, for coin flipping, P equals 0.50 because the chance of getting heads is 50%. P of F will be the complement to that. As we discussed in chapter 4, you either have something occur, the complement is that it did not occur. So if the success does not occur, we call that the failure. And so then the probability of failure, 1 minus P, would be in this case also 50% because it's a 50-50 chance. But let's say, for example, I had a coin that was weighted to get heads more often. Maybe it gets heads 80% of the time, and that's a success, and it gets tails 20% of the time. But the P and 1 minus P, these are complements because you either have success or failure, one or the other. And N is the fixed number of trials. So if I'm flipping a coin 10 times and seeing how many times I got heads, then N would be 10. So this is just to get some notation so that we can write about and talk about this stuff. Slide 1 of 3. So the notation following up, X is a specific number of successes in N trials. So X can be any whole number between 0 and N inclusive. If I flip a coin 10 times and I look at how many times I got heads, the least I could get heads is 0, and the most times I could get heads is 10, and I might get it any number in between. P is the probability of success in one of the N trials. In my case of my coin that's more likely to get heads, maybe 80% that I get heads. Q is the probability of a failure in one trial. So if it's 80% success chance, it's 20% failure chance. Then P of X, where X is the number of times you had a success, is the probability of getting exactly N successes among the N trials. So for in my example of flipping a coin, P of 7 would equal the probability of getting heads 7 times when I flip the coin 10 times. So in a binomial distribution, you are repeating a procedure n number of times. Every time you do it, it's independent from all the other times, and there's a success and a failure as a result, and P is the probability of the success and Q is the probability of the failure. Then P of X would be like P of 2, P of 5, P of 7. P of 7 is the probability that you had 7 successes in your 10 tries. So P of X is the probability of having X successes in the 10 trials. Questions, comments, discussions? All right, let's see what their third slide looks like. It's a big paragraph, basically. As I was saying, success doesn't necessarily represent something good. It's just one of the 2 possible outcomes that's labeled that way. And be clear when you're doing a binomial probability distribution that X and P are constant in the sense that they both refer to the same category being called a success, like heads. Like X is the number of heads and P is the chance of getting a head. That both of them have to do with being a success. Probability of success, X is the number of successes. All right, so here's our first challenge. Maybe I've lost all of you and you can't keep up, but give it a try. Can you think of any example of a situation of repeated trials of doing something that would lead to a binomial probability distribution? Whether you're going to share it or not, just try to think of one. See if you understand this idea enough that you could come up with a simple example, like the example I gave where you flip a coin 10 times and count how many times you got heads. So see if you can think of something like that. And if you're willing to share it, great, and we can look at it and talk about it. So if you're willing to share an idea of a possible example, it doesn't have to be right, but it's for the purpose of discussion, then unmute your mic or type in a chat. But give it a try, even if you're not willing to share it. See if you can think of one. Give it a try.
Maybe with dice.
Okay, using dice.
Mm-hmm.
All right, so what is the procedure that leads to an outcome? You roll one die or two dice or what?
Yeah, we can roll two dice and like see what is the probability of getting pairs, like yeah, one pair, like even numbers.
Okay, so that is a situation where we could calculate a probability. Let me ask you this. There were 4 requirements for it to be a binomial probability distribution. When you're rolling the dice to see if you get pairs, what do the outcomes look like? Like what's a possible outcome?
1 out of 6.
Well, not what's a probability, but like what does an outcome look like? Like, for example, when I was flipping a coin, an outcome is that I got heads. When I was rolling one die, outcomes where I got 1, 2, 3, 4, 5, or 6. So what do your outcomes look like?
Oh, no, I don't know.
Well, it sounds like you're saying you're looking at what did the dice give you? Like, did I get 2 2s or a 5 and a 7 or something like that, right?
Mm-hmm.
So to have a binomial distribution, there can only be 2 outcomes, heads or tails.
Okay.
So you could use your example if instead your outcomes were that the total of your dice were either odd or even.
Or even. Oh, okay. Yeah.
Does that make sense?
Yes, it does.
Then you would have a probability, then you'd have a binomial outcome at least. So then the question is, every time you roll the dice, are those independent? Well, sure, if I get odd or even on one roll, I'm not expecting that would affect that on a different roll, right?
Mm-hmm. Yeah.
Then you would need to repeat that trial n times. Like let's say you roll the dice 10 times and you see one of those is called a success, like maybe getting an even number is a success. Does that make sense?
Yes.
Okay, so that means that you would be looking at how many times you had a success between the 10 times that you rolled the dice. Does that make sense?
Okay. Yes. Yeah.
So here's the big question that's making this one challenging. Every time I roll the die, does the probability of getting an even number stay the same every time?
No, I don't think so.
What do you guys think? Anybody willing to chime in on this example for the purpose of discussion? We're trying to see, is this an example of a binomial distribution? So what I've been doing is I've been trying to have us kind of think about these 4 requirements. The procedure has a fixed number of trials. We're going to say you're going to roll the dice 10 times. 2, the trials must be independent. Every time you roll the die, what you got doesn't have any effect by what you got on other times that you rolled the die. They're independent from each other. 3, the trial must have all outcomes classified in exactly 2 categories. So we're saying that the 2 categories are I got an even total or I got an odd total. Like 7 would be an odd total. Snake eyes, 2, that would be an even total. So even or odd, and we're going to call even a success. So then the last one, as I was just asking, number 4, and if we can meet this, then this is a binomial distribution. If not, then it is not a binomial distribution. Is the probability of a success remaining the same in each trial? Meaning every time of the 10 times I roll the dice, every time I roll that, is the probability to get an even result the same? Or does it change from time to time? What do you guys think? So sorry, I'm not sure who was offering this example. It's a great example, but your feeling is that it's not the same chance to get an even every time you roll the die, or it is? What do you think?
I I don't know. I don't think it I think that can change. It can change like every time that you roll the dice, you can either have even, or you can either have what's the other, even
Odd.
and odd. Yeah.
Yeah. So let's say we were going to roll the dice once and we said, what's the chance I get an even? And we had some way to calculate that. We could actually probably try to do that with our skills from chapter 4, but it's a pretty hard chapter 4 problem. But we don't have to actually do these probabilities in this chapter. So let's assume that the chance of getting an even, well, first of all, even and odd sounds like it's 50-50, but I really don't think it is. And the reason it could be, but I'd have to do it because it's more complicated, because not all the die results are equally likely. It's very hard to get a 2 or a boxcar is a 12. The most common roll is a 7. Well, 2 and 12 are the hard ones. They're both even. A 7 is an odd result, and it happens 6 times more likely than getting a 2. And so the individual results are all mapped out, and we'd have to look at all those and add up how many of them, the probabilities of the odds versus the probability of the evens. But let's just say that the probability of getting an even number is 40%, and that's a success. So when I roll 2 dice, the probability that I get an even total is 40%. Would that 40% probability of getting even be different one of the other times I roll the dice? Or would it stay 40% chance of getting an even every time of those 10 times I roll the dice? What do you think?
I still think that it can change.
And how
Like
would
maybe like lower, because I know that getting odds it's more common to like getting
that's why I was
odds.
saying that the even might be 40% versus an odd being 50%.
Oh, okay. So then it can stay. Yeah.
Yeah, once you know when you roll the dice what the chance of getting an even is, it may not be 50-50. It might be 40% or something like that. But once you know that, well, that's not going to change every time you roll the dice. The chance to get an even when you first roll the dice is going to be the same as the chance to get an even when you roll the second roll or the third roll. So what number 4 is saying there, the probability of a success remains the same in all the trials. That means for our example, the probability of getting an even total remains the same every time in those 10 times that I rolled the dice. And that's true. So actually rolling the dice and seeing if you get an even or an odd is an example of a binomial probability distribution. Questions, comments, discussions about that?
Yeah, I think that with this example, I can have it more clear.
So was Randy was asking about if the dice are weighted or something like that. Yeah, it might be 50-50. I'd have to look. There's a 1 out of 6 chance of getting a 7. There's a I think it's 5 out of 32 chance of getting a 6 or an 8. There's a 4 out of 32 chance of getting a 3 or a 9. It kind of goes, I'm sorry, a 4 or a 9. So each different result has a different probability. We'd have to add up all the odds and evens. It wouldn't be too hard. It's just not worth bothering with. But definitely every time you make the roll, the chance of a success with the same pair of dice will stay the same through each of the 10 times that you try the roll. So this is a probability distribution. All right, we're up to slide number 8. Out of 36. We probably won't get to them all as usual. But here's one example in which they have 8 slides. So this is their example to really try to help us think about the notation and this idea. When an adult is randomly selected with replacement. That's a term from chapter 4, meaning that you could choose, you put the adult back into the people that were chosen from when you choose again later, and you might have the possibility of picking that same adult again. So when an adult is randomly selected with replacement, there's an 85% probability that this person knows what Twitter is, based on results from a Pew Research survey, which was probably done a few years ago. Suppose that we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. So if I randomly select 5 people, and we're going to just go to the population and grab somebody, and then maybe a day later, we're going to go grab somebody else, we may get the same person again. What's the chance that 3 of those 5 people know what Twitter is when an individual has an 85% chance of knowing what Twitter is when selected? That's an example of a probability distribution. I think they're going to discuss it, so let's look at the slides. So first they say, A, does the procedure result in a binomial distribution? So we have to look at those 4 criteria. B, if this procedure does result in a binomial distribution, identify the values of n, x, p, and q. So they're not asking us to actually do any calculations here. They're just helping us understand the notation and the requirements of binomial probability distributions when given an example to think about. All right, so first, the procedure does satisfy requirements for a binomial distribution as shown below. 1, there's a fixed number of trials, 5. 2, these are independent events. Picking somebody on one trial has no effect on when I pick somebody the second time. So they're independent from each other. 3, each of the 5 trials has 2 categories of outcomes, success and failure, where knowing Twitter, what Twitter is, or not knowing what Twitter is are our success and failure. And for each randomly selected adult, for number 4, there's an 85% chance of picking somebody that knows what Twitter is, and that remains the same every time I pick my 5 people. 85% on the first one, second one, third one, all the way to the 5th one. So those are the criteria for a binomial probability distribution, so that's what we have here. Questions about that at all? All right, so number 2, having concluded that the given procedure does result in a binomial distribution, we now proceed to identify the values of n, x, p, and q. We just have to know what those things were defined to be. So as it says, number 1, n was the number of trials, which in this case is 5. We are asking 5 people if they know what Twitter is. X will be how many people said they did out of the 5. So X is a number, 0, 1, 2, 3, 4, 5. That's a variable. We want the probability of exactly 3 who know what Twitter is. So X is 3. Meaning of those possibilities, 0 through 5, for how many knew what Twitter is, one possibility would be that 3 of them did. So we're saying that would be the X variable in the case for the probability we're calculating in this example. But in general, X is a variable, and it could be any of the numbers from 0 to 5, 3 being one of those, and we want to see how likely that is. If you get inspired with a question through all of this, then of course, feel free to unmute your mic and interrupt me and say, hey, Mr. Willett, I have a question. And I'm happy to stop and discuss it. So P is the next thing on the list, which is the probability of success. And that was given to us to be 85%. So P equals 0.85. The probability of failure, which is what they use the Q letter for, would be the complement for that. So if it's 85% success, then it's 15% failure, or 0.15. So those were the 4 things. So now it's very important to be sure that X and P, the number of successes and the probability of success, refer to the same concept of success. In this example, success was knowing what Twitter is. So X should be how many people who knew what Twitter is, and P should be the probability of knowing what Twitter is. They refer to the same outcome. So that was slide 8 to 6 of 8. Then they sort of go off on a detour, and I don't know where 7 and 8 are. Again, sometimes these slides are a little flawed. So I just wanted to point that out. If you're confused, so am I. I think they may come back and do 7 and 8 later down the list. I don't remember. It's been a while since I've looked at these slides. But it looks kind of funny that they say, here's 6 out of 8, and then they seem to change topics. I think they come back to it again. So treating dependent events as independent. So what does that mean? When sampling without replacement and the sampling size is no more than 5% of the size of the population, you could treat the selections as being independent, even though they're actually dependent. So this sounds a little confusing. How does this relate to the example that we were just looking at? Well, they said when we were picking people, and I mentioned this at the time, that they were picking them with replacement. The fact that after you talked to one person, you replaced them in the population, and then you could technically pick them again and ask them the same question again, that made every time you picked a person independent from every other time you picked a person, because it was with replacement. But the reality is, if you're talking to people and getting their opinion, or if you have a large population, you're really assuming you're not going to talk to the same person twice. And if you did, you may not want to do that. Then you'd actually be picking without replacement, and those would technically not be independent events. Because when you first talk to the group, and you talk to a particular person, picked a person from the group to talk to, well, then when you go to the group the next time, that person is no longer there. So the probability might change a little bit, and you can't get that same person again. So those are not independent events anymore. So that's what they're talking about here. So they're saying that when sampling without replacement, like if you are picking people from a population and you're not talking to the same person twice or replacing that person into the population when you choose another person, you can still pretend that those are independent events as long as the amount of people you're talking to is small compared to the population. As long as the things you're sampling are small compared to the group that you're sampling from, the population, well, then even if you didn't put one back in, it didn't affect things enough to matter. It doesn't affect things enough. So if I'm talking to everybody at DVC and there's 30,000 students, well, if I talk to one student and then only after that, there's only 29,999, and then I pick another one randomly, the probabilities haven't changed that much. So you can really just treat it as if you put the person back in and that these were independent events, which means you can still, in this case, consider it a binomial probability distribution. And they're giving you criteria here. If the sample size is no more than 5%. So if I'm talking to students at DVC and there's 30,000 of them, as long as I don't talk to more than 5% of that 30,000, which would be like 1,500 or something, as long as I don't talk to more than 5% of the population, it doesn't matter if I don't talk to the same person twice or allow that to happen. Then there's a bunch of formulas we don't want to use. So at this point, I'm going to want to step away from the slideshow, because instead I'm going to want to have us rely on StatCrunch to do these kind of calculations. So they're showing you here the probability of a particular number of successes can be calculated with this formula. If you have a binomial probability formula, a binomial probability distribution, then this formula allows you to determine what the chance of getting X successes out of your N trials might be with a formula. You can determine each of those probabilities. but we're going to use the StatCrunch calculator for that. So finally, there it is, example 7 of our 8. So now they're going to get back to our example. Let's try to finish those up at least. And let's just assume we use the formula that we would instead do on StatCrunch, or maybe we'll even do it on StatCrunch to confirm that they get the same thing. So it's saying, all right, given that there's an 85% probability that you know what Twitter is, and you're going to choose 5 people, our goal was to determine the probability that 3 of those 5 know what Twitter is. And we've already assigned the variables. We're trying to find, we want to find P of 3, the probability of having 3 Twitter knowing people out of our 5. And they're saying to apply the formula, but we're going to not bother. We'll let them do that work. And we know N is 5, X is 3, P is 85, and Q is 15 as a percent. So then they just plug into that nasty formula, do a bunch of stuff, and they get 13.8%, or 0.138 rounded to 3 significant digits, or 3 decimal places. So they conclude that the probability of getting exactly 3 adults who know Twitter among 5 randomly selected adults is about 14%, a little under 14%. Now that's getting exactly 3. You could get 4 or 5 or 2 or 1 or 0. Maybe you happen to pick 5 people that don't know what Twitter is. That's not very likely, but it's possible. We don't know. Maybe all 5 of them will know what Twitter is, but based on an 85% success rate on individuals, the probability of getting 3 out of the 5 is a little under 14%. Now they also say you could use technology to do this, so we'll say yes, thank you. That's what we'll do. We'll use StatCrunch or whatever technology you're using to calculate these binomial probabilities. And they show sort of slides for different possibilities. They don't have StatCrunch here for some reason. Maybe this was before they started to use StatCrunch much. Whoops, that's supposed to be an N. So that's what we'll use, but you could do it in Excel or a program called StatDisk or Minitab, or using a TI 83 or 84 calculator. And what you can see was what I showed you in our beginning example. You end up with a probability distribution. So this is a binomial, but it's also a probability distribution. And like the one I did in the beginning with rolling a die and seeing what number you got on the die, the possible outcomes are listed here, and then their probabilities are listed next to them. And you can see that in this case, the probability of having 3 successes was the 0.138. So if you didn't want to use this formula like this to get the 0.138, they're showing you that you can do it in technology and then see from technology, oh, getting 3 out of the 5 successes has that probability outcome. In all of the technologies, they had that same result. Then it's going back to an overtime rule from before. We previously noted that between 74 and 2011, this was from an early example, there were 406 NFL football games decided in overtime, and 252 of them were won by the team that won the coin toss. Is the result of 252 wins in 460 games equivalent to random chance, or is it significantly high? So I'm just going to look at this quickly, and then we'll do a problem in StatCrunch. So it says, okay, well, we have a 50-50 chance of success. We had 460 trials, and we want to find the probability of being 252 or more. Significantly high means that high or more is challenging. And they talk about using StatDisk or technology to do that. In this case, one of the choices to have that many or greater, and StatCrunch will tell us this also, and I'll show you how in a second. What do we got? We got about 9 minutes left, so I better get to that quickly. Anyway, so that's 2/3 of the way through the slides. Feel free to check out the rest of the slides because you can get all of these PowerPoints from the website. But that's what I wanted to cover from the slides. And now I would like to go and maybe look at an example homework problem for you so we can see what this looks like on a homework assignment. So let me close the slideshow. And now let's hop over to the homeworks. Okay, so this is the homework that's due next Sunday on chapter 5, sections 1 through 3. We've been discussing section 2. And so I've previously identified that 18 is a good problem to look at because that's from 2. But let's see if I can enter back in. And let's do a similar question. All right, so here's a question. This is number 18 from the homework set, and it is from section 2. Assume that when adults with smartphones are randomly selected, 41% use them in meetings or classes. If 10 adult smartphone users are randomly selected, find the probability that at least 8 of them use their smartphones in meetings or classes. At least 8 of them. That means 8 or 9 or 10 of the 10 people chosen. Okay, well, so this is definitely challenging. So I will point out that we could do some of our annotation stuff here, but notice they're just describing a situation, and then we're supposed to recognize that this is an example of a binomial probability distribution, and that we can then use those tools or formulas to determine this probability. So I would do things like I would point out that n is equal to 8. We are picking 8 people, and so that's the number of trials. And so it's a success. It says we're looking at how many people use their smartphone meetings and classes. And so that means that X is equal to number of people using phone in class out of the 8. That's a success.
Why?
So a success is using a phone in class. Question?
Yeah, I have a question. Sorry.
Yeah.
Why would N be 8 if we're randomly selecting 10 adults?
Oh, you're absolutely right. Thank you. I looked at the 8 instead of the 10 right above it. X would actually be 8. So thank you for fixing me. Let me adjust that. Getting my 2 numbers mixed up. Okay, yeah, N is 10 and X equaling 8, and I should say or more, is the people using phones. That's a success. And so P is the probability that they use a phone. That's given at 41% or 0.41. And Q would be the probability of not using phone in class, would be the complement, or 0.59. Now, we don't really have to identify the P and the Q technically, at least the P we do, but the Q is used in the formula, but it's not really used on StatCrunch. We mainly just need to know what is the probability of success, what is the number of trials, and what's the thing we're calculating. Questions about that? All right, so we could use their formula, but we are, of course, going to try to avoid that. So what would I do? Well, there's no data that they've given me. This is just a description of a situation. And so I'm going to open StatCrunch directly. In other words, I'm not opening data in StatCrunch. I'm just going and opening a blank version of StatCrunch in order to do a calculation. So our 2 tabs for StatCrunch use are Stat and Graph. And we want to do a calculation, so we're going to go to Stat and go to Calculators. And as you see here, one of them is binomial. So we want to go to Stat, Calculators, Binomial, and look at the binomial distribution calculator. So this is it. It has 5 little windows. And basically 4 of them have numbers in them. And if we fill in the values for any 3 of those 4 and hit compute, it will then fill in the 4th one for us. So n, that's why we need to know what n is and what p is and what x is describing and things like that. All right, so in this situation, they have it as a default where n is 10 and p is 50%. What is n in our problem here?
10.
10. And what is the probability of a success, the p-value?
0.41.
Yeah. So then the probability we are asked to calculate is the probability of getting at least 8. We have to translate at least 8 to mean that x is greater than or equal to 8. Meaning 8, 9, or 10. 8, 9, or 10 would be at least 8. 8 or more. Does that make sense? And then it'll do it for us. Now, the nice thing is it shows you graphically. It'll highlight in red the values that are at least 8, 8, 9, and 10. And those 3 together with each, with these stats, all together added up, it produces this probability, meaning there's looks like 1.5% chance of getting 8 or more people that know what Twitter is, if individually there's only a 41% chance and you look at 10 of them. Then the chance that 80% or better, 8, 9, or 10, know what Twitter is when less than half of the people do, according to this number, that would then suggest, sorry, I switched back to our Twitter example, use smartphones in class, that would suggest that there's less than a 2% chance that 8 or more people in a class will be using their smartphones or in a meeting. So they want this probability rounded to 4 decimals. So let's go to the 4th place. The 4th place is a 7. No, I went too far. It's a 5. 0, 1, 4, 5. So there's the 4th place. The 4th place is a 5, and the number after it is a 7. So I need to round the 5 up to a 6. So I'll drop that in here, back up on the 5 and make it a 6. And that should be what we want. All right, so lots to discuss here. We're running out of time at this point. Here is an example of a homework problem in which we had to recognize that this is a binomial probability distribution, and we had to go to the tool in stat in order to use this calculator for binomial distributions and know what a success, what probability was, P, know the number of trials, and formulate the probability they asked about of it being at least 8 of them using smartphones or having at least 8 successes into being x being greater than or equal to 8, and then it calculated that probability for us. And I could do anything here. I could calculate the probability of getting exactly 8. I could get the probability of getting exactly 4, which looks like that's the most common result. That's going to happen 25% of the time that 4 people in the meeting are going to use the smartphones, stuff like that.